In order to implement linear regression, the first key step is for us to define something called a cost function. This is something we'll build in this video. And the cost function will tell us how well the model is doing so that we can try to get it to do better. Let's look at what this means. Recall that you have a training set that contains input features X and output targets Y. And the model you're going to use to fit this training set is this linear function f(w_b) of x equals w times x plus b. To introduce a little bit more terminology, the w and b are called the parameters of the model. In machine learning, parameters of a model are the variables you can adjust during training in order to improve the model. Sometimes you also hear the parameters w and b referred to as coefficients or as weights. Now, let's take a look at what these parameters w and b do. Depending on the values you've chosen for w and b, you get a different function f of x, which generates a different line on the graph. And remember that we can write f of x as a shorthand for f(w_b) of x. We're going to take a look at some plots of f of x on a chart. Maybe you're already familiar with drawing lines on charts, but even if this is a review for you, I hope this will help you build intuition on how w and b, the parameters, determine f. When w is equal to 0 and b is equal to 1.5, then f looks like this horizontal line. In this case, the function f of x is 0 times x plus 1.5, so f is always a constant value. It always predicts 1.5 for the estimated value of y. So y hat is always equal to b, and here b is also called the y-intercept because that's where it crosses the vertical axis or the y-axis on this graph. As a second example, if w is 0.5 and b is equal to 0, then f of x is 0.5 times x. When x is 0, the prediction is also 0, and when x is 2, then the prediction is 0.5 times 2, which is 1. So you get a line that looks like this. And notice that the slope is 0.5 divided by 1. So the value of w gives you the slope of the line, which is 0.5. And finally, if w equals 0.5 and b equals 1, then f of x is 0.5 times x plus 1. And when x is 0, then f of x equals b, which is 1. So the line intersects the vertical axis at b, the y-intercept. Also, when x is 2, then f of x is 2. So the line looks like this. Again, the slope is 0.5 divided by 1, so the value of w gives you the slope, which is 0.5. Recall that you have a training set, like the one shown here. With linear regression, what you want to do is to choose values for the parameters w and b so that the straight line you get from the function f somehow fits the data well, like maybe this line shown here. And when I say that the line fits the data, visually you can think of this to mean that the line defined by f is roughly passing through or somewhat close to the training examples as compared to other possible lines that are not as close to these points. And just to remind you of some notation, a training example like this point here is defined by x superscript I, y superscript I, where y is the target. For a given input xi, the function f also makes a predicted value for y, and the value that it predicts for y is y hat I, shown here. For our choice of a model, f of xi is w times xi plus b. Stated differently, the prediction y hat I is f of wb of xi, where for the model we're using, f of xi is equal to wxi plus b. So now the question is, how do you find values for w and b so that the prediction y hat I is close to the true target yi for many or maybe all training examples xi, yi. To answer that question, let's first take a look at how to measure how well a line fits the training data. To do that, we're going to construct our cost function. The cost function takes the prediction y hat and compares it to the target y by taking y hat minus y. This difference is called the error. We're measuring how far off the prediction is from the target. Next, let's compute the square of this error. Also, we're going to want to compute this term for different training examples I in the training set. So when measuring the error for example I, we'll compute this squared error term. Finally, we want to measure the error across the entire training set. In particular, let's sum up the squared errors like this. We'll sum from I equals 1, 2, 3, all the way up to m. And remember that m is the number of training examples, which is 47 for this dataset. Notice that if we have more training examples, m is larger, and your cost function will calculate a bigger number since it's summing over more examples. So to build a cost function that doesn't automatically get bigger as the training set size gets larger, by convention, we will compute the average squared error instead of the total squared error. And we do that by dividing by m like this. Okay, we're nearly there. Just one last thing. By convention, the cost function that machine learning people use actually divides by 2 times m. The extra division by 2 is just meant to make some of our later calculations a little bit neater, but the cost function still works whether you include this division by 2 or not. So this expression right here is the cost function, and we're going to write j of wb to refer to the cost function. This is also called the squared error cost function, and it's called this because you're taking the square of these error terms. In machine learning, different people will use different cost functions for different applications, but the squared error cost function is by far the most commonly used one for linear regression, and for that matter for all regression problems, where it seems to give good results for many applications. So just as a reminder, the prediction y hat is equal to the output of the model f at x. So we can rewrite the cost function j of wb as 1 over 2m times the sum from I equals 1 to m of f of x I minus yi, the quantity squared. Eventually, we're going to want to find values of w and b that make the cost function small. But before going there, let's first gain more intuition about what j of wb is really computing. At this point, you might be thinking, we've done a whole lot of math to define the cost function, but what exactly is it doing? Let's go on to the next video where we'll step through one example of what the cost function is really computing that I hope will help you build intuition about what it means if j of wb is large versus if the cost j is small. We've seen the mathematical definition of the cost function. Now let's build some intuition about what the cost function is really doing. In this video, we'll walk through one example to see how the cost function can be used to find the best parameters for your model. I know this video is a little bit longer than the others, but bear with me, I think it'll be worth it. To recap, here's what we've seen about the cost function so far. You want to fit a straight line to the training data, so you have this model fwb of x is w times x plus b. And here, the model's parameters are w and b. Now, depending on the values chosen for these parameters, you get different straight lines like this. And you want to find values for w and b so that the straight line fits the training data well. To measure how well a choice of w and b fits the training data, you have a cost function j. And what the cost function j does is, it measures the difference between the model's predictions and the actual true values for y. What you see later is that linear regression would try to find values for w and b that make j of w be as small as possible. In math, we write it like this. We want to minimize j as a function of w and b. So now, in order for us to better visualize the cost function j, let's work with a simplified version of the linear regression model. We're going to use the model f(w) of x is w times x. You can think of this as taking the original model on the left and getting rid of the parameter b, or setting the parameter b equal to 0, so it just goes away from the equation. So f is now just w times x. So you now have just one parameter w, and your cost function j looks similar to what it was before, taking the difference and squaring it, except that now f is equal to w times xi, and j is now a function of just w. And the goal becomes a little bit different as well, because you have just one parameter w, not w and b. So with this simplified model, the goal is to find a value for w that minimizes j of w. To see this visually, what this means is that if b is set to 0, then f defines a line that looks like this. And you see that the line passes through the origin here, because when x is 0, well, f of x is 0 too. Now, using this simplified model, let's see how the cost function changes as you choose different values for the parameter w. In particular, let's look at graphs of the model f of x and the cost function j. I'm going to plot these side by side, and you'll be able to see how the two are related. First, notice that for f subscript w, when the parameter w is fixed, that is always a constant value, then fw is only a function of x, which means that the estimated value of y depends on the value of the input x. In contrast, looking to the right, the cost function j is a function of w, where w controls the slope of the line defined by fw. So the cost defined by j depends on a parameter, in this case, the parameter w. So let's go ahead and plot these functions fw of x and j of w side by side, so that we can see how they are related. We'll start with the model, that is the function fw of x on the left. Here, the input feature x is on the horizontal axis, and the output value y is on the vertical axis. Here's a plot of 3 points representing the training set at positions 1, 1, 2, 2, and 3, 3. Let's pick a value for w, say w is 1. So for this choice of w, the function fw looks like this straight line with a slope of 1. Now, what you can do next is calculate the cost j when w equals 1. So you may recall that the cost function is defined as follows. It's the squared error cost function. So if you substitute fw of xi with w times xi, the cost function looks like this, where this expression is now w times xi minus yi. So for this value of w, it turns out that the error term inside the cost function, this w times xi minus yi, is equal to 0 for each of the 3 data points. Because for this data set, when x is 1, then y is 1. When w is also 1, then f of x equals 1. So f of x equals y for this first training example, and the difference is 0. Plugging this into the cost function j, you get 0 squared. Similarly, when x is 2, then y is 2, and f of x is also 2. So again, f of x equals y for the second training example. In the cost function, the squared error for the second example is also 0 squared. Finally, when x is 3, then y is 3, and f of 3 is also 3. In the cost function, the third squared error term is also 0 squared. So for all three examples in this training set, f of xi equals yi for each training example I. So f of xi minus yi is 0. So for this particular data set, when w is 1, then the cost j is equal to 0. Now, what you can do on the right is plot the cost function j. And notice that because the cost function is a function of the parameter w, the horizontal axis is now labeled w and not x. And the vertical axis is now j and not y. So you have j of 1 equals to 0. In other words, when w equals 1, j of w is 0. So let me go ahead and plot that. Now let's look at how f and j change for different values of w. W can take on a range of values, right? So w can take on negative values, w can be 0, and it can take on positive values too. So what if w is equal to 0.5 instead of 1? What will these graphs look like then? Let's go ahead and plot that. So let's set w to be equal to 0.5, and in this case, the function f of x now looks like this, is a line with a slope equal to 0.5. And let's also compute the cost j when w is 0.5. Recall that the cost function is measuring the squared error or difference between the estimated value, that is y hat I, which is f of xi, and the true value, that is yi, for each example I. So visually, you can see that the error or difference is equal to the height of this vertical line here when x is equal to 1, because this little line is the gap between the actual value of y and the value that the function f predicted, which is a bit further down here. So for this first example, when x is 1, f of x is 0.5. So the squared error on the first example is 0.5 minus 1 squared. Remember, the cost function will sum over all the training examples in the training set. So let's go on to the second training example. When x is 2, the model is predicting f of x is 1. And the actual value of y is 2. So the error for the second example is equal to the height of this little line segment here. And the squared error is the square of the length of this line segment. So you get 1 minus 2 squared. Let's do the third example. Repeating this process, the error here, also shown by this line segment, is 1.5 minus 3 squared. Next, we sum up all of these terms, which turns out to be equal to 3.5. Then we multiply this term by 1 over 2m, where m is the number of training examples. Since there are 3 training examples, m equals 3. So this is equal to 1 over 2 times 3, where this m here is 3. If we work out the math, this turns out to be 3.5 divided by 6. So the cost j is about 0.58. Let's go ahead and plot that over there on the right. Okay? Now let's try one more value for w. How about if w equals 0? What do the graphs for f and j look like when w is equal to 0? It turns out that if w is equal to 0, then f of x is just this horizontal line that is exactly on the x-axis. And so the error for each example is a line that goes from each point down to the horizontal line that represents f of x equals 0. So the cost j when w equals 0 is 1 over 2m times the quantity 1 squared plus 2 squared plus 3 squared, and that's equal to 1 over 6 times 14, which is about 2.33. So let's plot this point where W0 and J of 0 is 2.33 over here. And you can keep doing this for other values of W. Since W can be any number, it can also be a negative value. So if W is negative 0.5, then the line F is a downward sloping line like this. It turns out that when W is negative 0.5, then you end up with an even higher cost around 5.25, which is this point up here. And you can continue computing the cost function for different values of W and so on and plot these, right? So it turns out that by computing a range of values, you can slowly trace out what the cost function J looks like. And that's what J is. To recap, each value of parameter W corresponds to a different straight line fit, f of x, on the graph to the left. And for the given training set, that choice for a value of W corresponds to a single point on the graph on the right. Because for each value of W, you can calculate the cost J of W. For example, when W equals 1, this corresponds to this straight line fit through the data, and it also corresponds to this point on the graph of J, where W equals 1 and the cost J of 1 equals 0. Whereas when W equals 0.5, this gives you this line, which has a smaller slope. And this line, in combination with the training set, corresponds to this point on the cost function graph at W equals 0.5. So for each value of W, you wind up with a different line and its corresponding cost J of W. And you can use these points to trace out this plot on the right. Given this, how can you choose the value of W that results in the function f fitting the data well? Well, as you can imagine, choosing a value of W that causes J of W to be as small as possible seems like a good bet. J is the cost function that measures how big the squared errors are, so choosing W that minimizes these squared errors, makes them as small as possible, would give us a good model. In this example, if you were to choose the value of W that results in the smallest possible value of J of W, you'd end up picking W equals 1. And as you can see, that's actually a pretty good choice. This results in a line that fits the training data very well. So that's how, in linear regression, you use the cost function to find the value of W that minimizes J. Or in the more general case, when we had parameters W and B rather than just W, you find the values of W and B that minimize J. So to summarize, you saw plots of both F and J and work through how the two are related. As you vary W or vary W and B, you end up with different straight lines. And when that straight line passes close to the data, the cost J is small. So the goal of linear regression is to find the parameters W or W and B that results in the smallest possible value for the cost function J. Now in this video, we worked through our example with a simplified problem using only W. In the next video, let's visualize what the cost function looks like for the full version of linear regression using both W and B. And you see some cool 3D plots. Let's go to the next video.